In the last section, we discussed the way in which the term module should be defined, and we determined that the appropriate definition for the purposes of this course is a unit of resource that is customized to perform one type of information process very efficiently. Now, in the following sections, we're going to be discussing how the practical considerations that we discussed earlier will tend to constrain a complex learning system into a hierarchy of modules, with modules defined as discussed earlier. So, why would a system have modules, defined as separate units of information processing resources? Why shouldn't all the resources be blurred together so that you can't identify separate pieces? The primary reason is to make it possible to reduce the total information processing resources the system needs to perform all its features. All sorts of different information processes will be needed to perform all the system features, and to economize on resources, similar information processes are collected into groups, independent of what feature they're supporting. And a module is created with its resources optimized to perform that type of process very efficiently. With this definition, a module always supports lots of different features, with the result that we've already discussed extensively for computer systems. The application architecture is nothing like the resource architecture. Let's think for a moment about system operations in terms of condition detections. A system has to detect lots of different conditions to guide its behaviors. And let's suppose in this diagram every red dot represents a condition the system needs to detect. Some of these conditions will be similar to each other. They may have some inputs in common, for example. So a group of conditions can be identified with a fair degree of similarity between the different conditions within the group. And there'll be many such groups. So you can divide up all the conditions into groups based on similarity. Then you can assign different resources to each group and optimize the resources assigned to one group to perform the type of condition detection of the group very efficiently. So each resource is a different module, detecting a different group of similar conditions. But there may be some smaller degree of similarity between the conditions detected by a number of different modules. So you can associate different groups of modules on the basis of this smaller degree of similarity. And because the degree of similarity, this smaller degree of similarity, you can share some of the resources. You can repeat this process based on an even smaller degree of similarity, and repeat it again until the degree of resource economy achieved is no longer useful. So, the need to economize on resources drives the existence of a modular hierarchy, although there's generally no obviously ideal way to define all the modules. You do the best you can on the basis of similarity. But however you define the modular hierarchy, there's an additional way in which resources can be saved. Sometimes, even after you've divided things up on the basis of similarity, the same simple condition may be needed to define higher conditions in several different modules, as I've indicated a possibility with the red dot. So rather than duplicate the resources to detect the same condition in both modules, the condition detection could be made in one module and communicated to the other. And that's what we call an information exchange between modules. These information exchanges may be valuable at many different levels in the hierarchy. So we've reached a number of conclusions about physical resource modules, just on the basis that we need to conserve resources. They need to be organized into a hierarchy in which higher level modules are made up of groups of more detailed modules, and we need to exchange information between modules. Now, in the next section, we'll look at how modifiability impacts this definition of modular hierarchy.